אז בשאלה הראשונה בתרגיל ראשון, השאלה היה לצייר את הגרף של ה-error היחסית, השגיאה היחסית, בין הנגזרת, הקירור של הנגזרת f of x plus h מינוס f of x, לחלק ב-h, כפונקציה של h, כש-f זה היה סינוס x, ולחשב את זה מול התשובה האמיתית. כן? ואז א', היו אנשים מה שהם עשו, שהם לקחו את הנוסחה האנליטית שקיבלנו בכיתה, כן? ועשו גרף של זה ועשו מינימיזציה של זה. ולא לזה התכוונתי. כי כל המטרה של התרגיל הזאת היה לראות שמה שאמרתי בכיתה היא לא שקר, כן? אז כל הרעיון הוא היה לאמת את הקירובים שעשינו בכיתה, ואמרנו שבעצם, אז אמרנו, כן, שבעצם השגיאה הולך בסקאלה לוגריתמית, log error, כפונקציה של ln h, אתה מקבל משהו בסגנון הזה, כן? עכשיו, וכל הרעיון היה לראות באיזה מידה זה נכונה, כן? ואז האנשים שפשוט כתבו את הנוסחה שזה אפסילון בריבוע פלוס 10 בחזקת מינוס 16 לחלק ב-h ועשו גרף של הפונקציה הזאת, זה לא סיפק את לא לזה התכוונתי, כן? כי אני יודע שאתם יכולים לצייר גרף באמצעות MATLAB, זה לא תרגיל ראוי, לא הייתי שואל שאלה כזאת טיפשית. ובאמת, כשאתם עושים את התרגיל הזה, אתה לא מקבל את זה. מה שקיבלתם זה זה.
אני יכולה רק לעצור, כאילו לומר באופן כללי, אנחנו יחסית מעט, יש למישהו בעיה אולי שתעביר את התרגול באנגלית?
אין לי בעיה.
יש למישהו כאן אבל שזה מפריע לו?
לי זה לא מפריע. יש בעיה. בסדר. Okay, we'll go to English. So what you get in practice was not a beautiful smooth curve, right? You got something that looked more or less like that. Why did you get something that looked more or less like that? Because what I said, in fact, is that this was times some random number, because it's very hard to know exactly. The truncation error sometimes is plus, there's some truncation error sometimes is minus, right? You don't know exactly what you're getting, and in fact, so there's this, and so when you're plotting it up, you're every time you change h by a little amount, you're seeing huge variations in because the last digit sometimes that you dropped was 8, and sometimes it was 7, and sometimes it was 6, and sometimes it was 5. So the amount of error you're making changes as a function of h as you change the last digit. So in fact, when I asked the question, what was the minimum? What was the minimum error you get? And so if you take that literally, the answer is 0. Because if this was the absolute log of the absolute value of error, but if you actually plot the error itself, what you'll see is that in this region, it's crossing 0, because it's changing sign. And that's why you're getting these huge oscillations here, because in log space, 0 is at minus infinity, is all the way down at the bottom of the, right? So since it's, and so in fact, the minimum error, in fact, not that that's the question I was meant to ask, but in fact the minimum error is 0. Because there are very specific values of h that give you 0 error. That's useless from a practical point of view, because you don't know what those values of h are, so you can't get zero error, right? It's just by happenstance, you know. The point is, what I meant to ask is this: there's an envelope here that the error, the envelope of the error is is going like this, because this number is plus minus 1, somewhere between plus and minus 1, and so the error, the envelope looks like something like this. It gets you a smooth curve, and then the minimum of that was at either 10 to the minus 12 if you had the symmetric one, and 10 to the minus 8 or something if it was the one-sided one. But in fact, so this is another lesson, is that this beautiful formula that I wrote down is in fact not right. It's a lie. But it's a useful lie, because it tells you what you need to know and not what's actually happening, which is a big mess, actually. So that's number one. Number two is there were other people who plotted the error up, and however, the way they did it is they used a function from MATLAB called fplot, which plots a function. Right? So they defined the function, which was this, minus cosine 1, or whatever, absolute value, mashallah, yeah. And what they got is they got the following beautiful graph. They got that. Why did they get that? That's wrong. Because in fact, we know that it increases for small h. When h gets very close to 0, it's supposed to go to infinity, the relative error. But they didn't get that. Why didn't they get it? Because MATLAB didn't get it, because MATLAB lied to them. And that's the whole point, that MATLAB lies. And that's why you have to be smarter than MATLAB. Because MATLAB, when you ask it to plot a function, what does it do? I mean, it doesn't know what the function's supposed to look like. It has no understanding. What it does is it plots up 40 points. And if it's smart, which is semi-smart, it says, is the curve smooth? And if it's not smooth, if it sees that there are oscillations, then it doubles the number of points or whatever until it thinks that it's reproducing the curve at some level. I don't know. I haven't looked at the code of actually how fplot ever works, but that's what's logical to do. And as soon as it decides that it's covered the function, it gives you the smooth curve that it's expecting you to get. So in fact, as long as the h's are reasonably sized, 1,000, 2,000, 3,000, 5, it's a perfectly smooth curve. So that's what fplot sees as a perfectly smooth curve, and that's what it gives you. And it doesn't say, well, I really should check what's happening at h is 10 to the minus 6, because that's stupid. Why would a function start misbehaving at a value of the argument of 10 to the minus 6 when h is 10 to the minus 6? No reason. So it doesn't waste its time checking things, because it has no way of knowing whether it happens 10 to the minus 6, happens 10 to the minus 12, never happens at all. It has no way of knowing. So it says a reasonable small value of h is maybe 1,000 or something like that. And if it sees no problems developing, then it just goes and gives you the beautiful smooth picture that it was trained to give you. And that's an absolute lie. And the only way to prevent the lie is you have to do it yourself. You can't use the automatic tool. The automatic tool is great when you're actually plotting a smooth function, and all you want to do is, you don't want to have to define the x, use linspace to define a set of x's and then call the function on that, right? The fplot is very convenient. But you can only use it when, in fact, what you're plotting is fairly smooth. Because if it's got any kinds of very subtle kinds of behaviors, fplot is too stupid to see them. And so that's, in fact, a beautiful example of how MATLAB can lie if you're not careful. All right. One other note from the homework. The last question, right, was to derive a formula for f prime, which was good to h to the fourth. And everybody got the basic idea, except that some, maybe, I don't know, 10% of the people had an algebra mistake. And that's perfectly fine. Everybody makes algebra mistakes. I make more than my share, right? It's not bad to make an algebra mistake. The problem is when you derive a beautiful formula like whatever it was, 12h, 8 of x of h minus f of x minus h plus minus f of x plus 2h minus f of x minus 2h. That was the formula, something like that, right? You derive that formula, and if you're me, what you do is you check it by doing exactly what we did in the first question, plotting up the error and seeing if it falls like h to the fourth, right? And then if you made a mistake and in fact you got that to be plus because you made a mistake, you'll catch it, right? And it's trivial to do. So whenever you derive analytic formulas, you should check them. That's the beauty of having the numerics, is the numerics checks, just like in the first question, the numerics tests the analytic approximations that we made, and with the epsilon squared and then the 1 over epsilon and stuff like that. Similarly here too, you derive a formula, check it out. It costs it costs a minute and a half, and you get saved from the algebra mistakes, which like somebody at my age is guaranteed to make, because everybody makes algebra mistakes. So if you derive a formula, if it's easy to check it out, there's no reason not to. That's the whole beauty of having MATLAB sitting there at your beck and call to do things like that. All right, so that was the lessons I learned from the first exercise. Right.
David?
Yeah.
When you plot the error, you added a term of 10 to the minus 16 divided by
Right.
h.
Right.
Don't you have to multiply that by some derivative?
Yeah, but it's order right. But since cosine 1 is an order 1, and
But generally it is important, right?
it could be, yeah, right. If it wasn't, if that term is, if the actual, well, in the relative error it drops out, right? Because it's that times it's that times the function, right? Because you're evaluating, it's the error in f. That's a truncation error in f, so it's proportional to f, right? It's 10 to the 16th minus 10 to the minus 16th times f itself. So when you calculate the relative error, actually it drops out. Turns out, whatever. Yeah, I mean, okay. I mean, the whole idea is to get a feel for the size of h's that are relevant, right? In the new Targil that I posted, part of the job in the new Targil is to write a Newton solver, right? And part in n dimensions, and part of writing the Newton solver is to generate the Jacobian matrix using numerical derivatives, right? So you have to pick a value of h to do that. And it's not critical what the value of h is, but you want to pick something reasonable. So 10 to the minus 6 or 10 to the minus 7 is a reasonable value for h, right? Not knowing anything else. And you don't know anything else because you don't know, you're running a general function that's supposed to be good for anything you put into it. So the point is to pick a reasonable value of h, and 10 to the minus 12 is too small, and 10 to the minus 2 is cutting it is a little too, you can afford a little better accuracy than that. So 10 to the minus 5th, 10 to the minus 6th, something like that is a useful kind of range of values of h that you should use to calculate the derivatives. All right. Are there any questions before I go on to other stuff. All right. So the one other thing I thought I'd talk about a little bit more about, because we didn't really. So we talked a little bit about sparse matrices, and they're important. That when you have a matrix, when we have it solving a linear system, if most of the elements in the matrix are zeros, then it makes a big difference if you use sparse matrices rather than using the full matrix. So just to show you how that works, and it's because it's a lovely example, and it's right? There's the matrix which has -2s along the diagonal. So let's take a 4x4 case, and has 1s on the super and subdiagonals. Right? So there's, I want 4x4, that's that, right? So the 0, 0, 0, 0, 0, 0. So this is not so sparse, actually, right? But in practice, right? I mean, right? I mean, we could do the same thing, NLN, and then there are 3 elements in each row, and if there's 100, if the matrix is 100 by 100, and there are only 3 elements in each row, then it's really a sparse matrix. All right? So the question is, what does the... And the whole point is that when you do the LU decomposition, L and U are sparse. And that is the critical thing, because that's what allows you to save all this time. So, in fact, what is the LU decomposition of this matrix? All right? So, if you work it out, I asked my friend MATLAB to work it out, and you get the following answer. L is, so it's 1, 1, 1, 1 along the diagonal, 0 upstairs, of course, and then it's -2, which is obvious because that's a -2, and this was a 1, 0, 0, oh, -1/2, sorry, this is -1/2, and this is 0, 0, this is -2/3, and this is -3/4. So that is L. So you see that it is also sparse. It only has elements on the diagonal, which is all 1 because it's a matrix of type L. It's a lower matrix, so the diagonals are always 1, that we knew. And it only has elements along the subdiagonal. And you work it out. And what you find out, of course, there's zeros downstairs. And what you get is -2 -3/2 -4/3 -5/4 1, 1, 1, 0, 0, 0. So this is also sparse because it only has elements along the main diagonal and the super diagonal, and nowhere else. So this is also a sparse matrix, and that's so the whole idea is that that now when you're back solving, there's only each operation you only have to solve an equation with 2 variables to do the back solving, so therefore the whole process is you have to solve n equations to solve for y, and then you have to solve n equations to get x. So there's something all along the lines of 2n operations to do the game, because you have to calculate L, you only have to calculate those values. There are order n of them, and to calculate U, you only have to calculate these values. Again, there's only n of them, so it's very quick. So the whole thing, instead of being n cubed, is order n. So that's the big savings, because that's the savings of n squared. Now, I mean, first of all, this is really beautiful. I mean, you have to have an aesthetic sense. So this matrix is a nice matrix, and L and U are just simply beautiful, because in fact, if you do the n by n case, what's on the subdiagonals? -1/2, -2/3, -3/4. What's the next one?
-4/5.
That's right, and it goes on all the way. to the end. So in fact, you can write it down analytically by just solving the case, the 4x4 case, either by hand or with MATLAB. You now know the general solution for all n. And the upper case is this is -2. This is -3. That's 1 over that. This is -3/2. That's 1 over that. This is -4/3. This is -4/4. The next one is -6/5, -7/6, and so forth and so on. So it's really gorgeous. I mean, you got to appreciate gorgeous things when they come around. And this matrix is a very important matrix because it's basically the matrix. It's got this 1 minus 2, 1, which is basically a second derivative. And when we get to write down differential equations, if we have a differential equation which involves a second derivative, which we're going to get eventually, then this matrix shows up all the time. And in fact, it has a beautiful thing. And in fact, there's a terminology you should know. This matrix is this is a tridiagonal matrix, or a flat alloxonie matrix, because it only has elements on the main diagonal, the superdiagonal, and the subdiagonal. And if you do an LU decomposition for any tridiagonal matrix, in fact, L looks like this. The numbers are different, but the structure of the L is the exact same, and the structure of U is the exact same. But if you have general elements along the diagonals, and you have general numbers there, but the structure is always the same, and therefore, solving this tridiagonal matrix, once you tell MATLAB that to use sparse matrices, then the L and the U are very beautiful and come out very quickly. So in fact, it was once even before. It's interesting that once upon a time there were special routines. People wrote special programs to solve tridiagonal matrices. That's before they did LU decompositions. LU decompositions were more recent invention, but people realized very early on that to solve a tridiagonal system is very simple. Just by even without using LU, just doing it by hand, there's a way to solve a tridiagonal system in time of order n, and they realized that very early, before they invented the whole LU business. But having the LU business just makes it just obvious that things are of order n, because things are only n numbers here and only n numbers there that we need to compute.
About U, is the superdiagonal always 1? If it's a
No. I don't think, no. That has to do, that has to do with the fact that the superdiagonal in this matrix was all ones.
But you meant that just generally only those two diagonals are non-zero, and
Right.
the other ones are.
Right. And in general, if you had, then you can generalize the concept of a tridiagonal matrix to something that has only elements on the top, the main and the first two, and the sub two, the two underneath the diagonal. Those matrices are called they're called banded matrices, because all the non-zero elements are in a band around the main diagonal. So after people realized that you could solve tridiagonal matrices easily, then they generalized this. You can actually solve banded matrices easily, and basically, and of course, the bigger the bandwidth, the more diagonals there are, the more expensive it is, and it grows like so the time is n. It's always proportional to n, but it's times the bandwidth squared. And now, when the bandwidth is order n, we're back to our n cubed. So that's how. So originally people wrote special programs for tridiagonal matrices, and then they wrote programs for general banded matrices, and then they discovered that you can do this all easily for general sparse matrices and save yourself all this. But there used to be special routines for tridiagonal matrices and banded matrices and all these things, and they're not very useful anymore. MATLAB doesn't bother with it anymore. Once upon a time, you would say this is a tridiagonal matrix and then solve it. But now you just have to tell what the sparse is. You do everything else. All right. That is okay. That is that. So the homework for this week is fairly straightforward. There are 3 questions again, except the 3 questions are getting more. They're having subsections into the question. The first question is to just solve for, I don't forget, the square root of 3 to 20 to 18 decimal plus 16 decimal places or something using Newton's method. That's very straightforward. The second question is to write a general Newton solver in n dimensions, including constructing the Jacobian, and then using it to solve a 2x2 system that has 5 different possible answers, right? Like the system we looked at in class had 3 possible answers. It had the minus 1, 0, and then it had the half, the square root of 3 over 2, and plus and minus, so there were 3 different answers. Here, this system I wrote down of 2 equations and 2 unknowns, in fact, there are 5 answers. And now the cute thing, so you can write a program you write a general Newton solver to solve any system. You can feed it this thing, and it works if you give it a good guess. And now the question is, what happens if you just give it any guess? So as I pointed out, you don't know where you're going to wind up. So the whole idea of the exercise, the last part of the exercise, is to pick a point, to do a scan of points in the x0, y0 space of your initial guesses, and say, okay, which one of the 5 solutions do you get when you start here? All right, and then you construct a matrix, which say you got to the 3rd solution here, and you got to the 3rd solution here, but if you start here, you get to the 4th solution, and here you get to the 4th solution, and here you get to the 2nd solution, and here you get to the 1st solution, and you build up a matrix of, depending on where you started, where you wind up. And you wind up in either solution 1, 2, 3, 4, or 5. And then you can plot this matrix using a MATLAB command called image scaled, which takes a matrix of numbers and makes a pretty picture out of it. And you do that, and you'll get amazing pictures. So that's that exercise, which is you'll get an amazing picture. And then the last thing, do I remember what the last thing was? Do I remember what the last thing was? I think I've already forgotten, because I did it this morning. That was a long time ago. Yeah, don't remember anymore. But it's also not shouldn't be very difficult. It's just more Newton's method and stuff. So homework is all about Newton's method. All right. So that's all. Unless if there are no questions, then
I have a general question.
Yeah.
You said that if you have a multivariable function and you divide its domain into discrete parts,
yeah,
then you can find all the solutions if you divide for enough parts. Let's say 100 or 1,000. But let's say I have a function with a bounded derivative, and I know the bound is very low. I know it's not going to change a lot. So is there like an easy way to know how much parts I should divide it?
Easy way? No. I've never thought about that question. So I don't know the answer.
The only idea I have is if the derivative is bounded.
Yeah, I hear what you're saying, and if the derivative is not small, then yeah, but then the function is sort of straight, like a straight line, more or less, or right, and so it's not going to do anything, right? So then you're going to, right? The things become interesting when the function is curved and has this, zero, and has minimum
No,
and
I didn't
maximum.
say constant. I said bound because if.
Yeah, but if the derivative is always bounded, so it can't can't have a maximum, it can't have a minimum, right? Can't even have the function's so boring that it's basically a straight line, more or less, or a plane, or something very close to a plane. So yeah, then Newton will work fine, but that's sort of that's the way things work. All right, so if that's that, okay, so I have nothing more to add, I think.
By the way, if that's the case, then when you solve a real-world problem, how can you be confident that you divided the domain into enough parts?
No, so that was the thank you. Now you reminded me what the last question was all about. Thank you. Now I remember the last question. No, in general, you don't have any guarantees, you don't have any assurances, and the only method you have is the method I described in class, which is what the last question is all about. Is you start somewhere where you know the answer. You introduce a parameter into the problem such that when the parameter is small or large or whatever, you know the solution. And so in the question is of the following type. You have, so in fact, I say you have, I forget, a 616 system, but let's talk about a 212 system that looks like the following. 0 equals x1 minus x1 squared minus c times alpha x1 y x2 minus alpha x1 x2, say. And 0 equals x2 minus, so some number minus x2 squared minus some other number minus c times beta x1 x2. Right? And really in the real problem there are 6 of them. So you have x3, 0 equals x3 minus x3 squared minus c times something x1 x2, something x1 x3, something x1 blah 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 blah. And the point is that when c is 0, this is trivial to solve because x equals 1, right? So that's totally trivial. And now, so the idea is that you start with c equals 0, you know what the solution is, and now you take c equals, say, 0.05 or something, 0.05 here, right? And now you give it as an initial guess the solution 1, 1 that you got here for this system, and there's no reason, since c is small, there's no reason that that's a bad guess, and you'll find the solution, right? And then once you find that solution, you change c to 0.10, using as an initial guess the solution you got for 0.05, and since that's close by, you should find the solution.
It's kind of like Euler's method, where it's kind of like you have the value of a function at the point, and then
right. You're adiabatically changing the parameter, so like it's a motion of the solution in space because you're slowly turning the crank, right? And as you turn the dial, that's c, then the solutions slightly change until something drastic happens. Unless something drastic happens. If there's a point in c where there's no solution, or the solution blows up, well, then there's nothing you can do. But as long as you're in a good region of parameter space, then small changes in c correspond to small changes in the solution, and you can track things. So if you just started out with c equals a half here, and tried to guess the values of x, the initial values for x1, x2, x3, x4, x5, x6, who knows whether it would work? It might work, it might not work, and you have no control over things. But here, you do. So, and that's the last question, is to see that that works. All right. So enjoy. So we don't meet next week, right? So ביום שלישי יש? חשבתי זה שבוע שלם, לא?